in the benefit of time. So I'll just go straight to the next talk, which will be by Prof. Judith Kinnaird, who will be talking on the Waterberg deposit. Judy, I will stop sharing my screen and then you can share yours and continue. Thank you very much.
Okay, can everybody see the screen and hear me?
Looks good, thank you.
Okay, so I want to present a generalized talk today, and I want to focus on the comparison between the Waterberg and other areas. And if anybody wants more mineralogical and geochemical data, I can provide papers and PhD theses. I want to thank my company colleagues listed here, and particularly my academic collaborators. Okay, so when we look at the northern limb, we see that the exposed northern limb of the Bushveld complex extends from the, oops, what have I done there? From the Tabazimbi-Murchison lineament up towards the what's shown on this screen as HRSZ, which is the Hout River shear zone. And it had been assumed that this exposed northern limb linked in a westward fashion with the Villanora segment of exposed upper zone shown there to the west. And then in 2011, PTM started drilling to the north of the Hout River shear zone, and many people said that they were just absolutely crazy. But what they saw was, here is the northern limb, here is the Hout River shear zone, and what they saw was this zone here in the geophysics map extending up as far as the Palala shear zone. So they actually drilled under the 2 billion-year-old Waterberg sediments, and they actually found something which looked like a succession of Bushveld rocks. So here in the top is the Waterberg sediments, and then immediately beneath them, something that looked like a Bushveld succession. So that suggests that this northern limb extends much further north. And in fact, geophysical studies by Carol Finn in the USGS in Denver and colleagues here in South Africa confirmed that mafic rocks, Bushveld rocks, continue under the Waterberg and Karoo sedimentary units considerably far westwards, and that we've got this very large northern part of the Bushveld complex with this northern lobe, a similar size to the eastern and western limbs. And so this confirmed the suggestion that I made back in 2005 and many others before me, that the Bushveld rocks went all the way up to the Palala shear zone, giving the total area of the Bushveld complex something like 90,000 square kilometers. So what is shown on Carol Finn's map here is little circles which show where Waterberg project drilled. So what PTM had found was what looked like Bushveld rocks to the north of the Hout River shear zone. So here's the northern limb extending from the Tabazimbi-Murchison lineament, the Hout River shear zone here. And this marks the boundary between the southern marginal zone of the Limpopo complex and the stable Archean craton. And it's a composite structure along which the southern marginal zone was thrust southwards between the Zimbabwe and the Capval Craton. This southern marginal zone is a granulite facies terrain, and within this southern marginal zone, there are several major shear zones. So we started to wonder, having found bushveld rocks beneath the 2 billion-year-old Waterberg red beds, we started to wonder, are these really bushveld rocks? If so, there must have been an awful lot of erosion very quickly to erode these bushveld rocks here and deposit the very thick Waterberg succession within about 50 million years. And I was personally doubtful that this was in fact a bushveld succession. And I began to wonder whether in fact it was of great dike age of 2.57. A lot of people started to draw a line between the Great Dyke and the bushveld complex, completely ignoring the Limpopo belt. But the condomagnetism, which is at 1.1 GA, did expand down from Zimbabwe down into South Africa. So one of the first things we wanted to know was whether this was in fact bushveld age. So one of my postgrads, Florian Huffman, extracted some minerals and did some age dating on these rocks. And we got dates from these mafic rocks using thorianite and zircon of 2.59 and 2.53, confirming that indeed these were bushveld aged rocks. So when we started to look at them, we divided them fairly easily into what we thought was an upper zone, a main zone, and a lower zone in establishing a stratigraphy. So that was all on the floor of granite gneiss, and you can see the sort of stratigraphy here. There's your Waterberg red beds, the upper zone, and then going down through what we originally called a main zone to what we originally called a lower zone, separated from a footwall of granophyllous and granite by marginal sills. So we've got our upper, we've got our upper zone, which is of ferrogabbro, ferronorite, and gabronorite. But rapidly differences started to emerge. Firstly, our upper zone on the Waterberg project might have been completely eroded away, so that there's none left. But there's generally a maximum thickness of about 500 meters. And compare that with what's seen in the Bellevue core just to the south of the Hout River shear zone that Ashwell and others looked at. And there's much thicker Waterberg, 1188 meters in the Bellevue core, and around about 2,000 meters in the eastern and western limbs. But the one of the first major differences that started to emerge is that there's no magnetite layers in the upper zone of the Waterberg, whereas there were 32 layers noted by Ashwell in the northern limb further south, and something like 26 in the eastern and western limbs. So there's a major difference started to appear. Also, there's a lack of apatite, so we can't make any comparisons with the zonation of the upper zone in the rest of the bushveld complex. And also we found that the minerals were compositionally more primitive than elsewhere. So our pyroxenes, for instance, that are shown there, have Mg numbers of 63 to 77, whereas Mg numbers in the northern limb are much less than that. And the upper zone in the Waterberg project lacks any anorthosite layers. So we concluded that it was similar to the upper zone elsewhere, but there were differences. So We then looked at what we thought was the main zone sequence below the main zone, and elsewhere, as in the everywhere else, it's the thickest zone on the Waterberg project, but it only varies from 400 to 850 meters thick, whereas it's more than 3,000 meters in the northern limb and up to 4,000 meters in the eastern limb. It's still dominated by gabbro-norite. We made comparisons with the work done by Lou Ashwell and others, looking at the succession in the Bellevue borehole shown here in the northern limb. Sorry, that would be the Hout River shear zone up here. And what Lou Ashwell noted was that when you look at the succession and you look at the magnetic susceptibility of the main zone, it's very much a quiescent zone for magnetic susceptibility. And then as you hit the upper zone where there's magnetite, magnetic susceptibility rises dramatically. So Ashwell drew his boundary between the main zone and the upper zone at this change in magnetic susceptibility. And we followed and we did the same thing for the Waterberg cores, even though where we drew the boundary was actually 100 meters or more below where you could see the first magnetite, which would be where Sachs would put the boundary. But it was very useful stratigraphic mark, and I'll come back to that in a moment. At the base of this unit, there is a troctolite, and the olivine in the troctolite and the breakdown of the olivine leads to magnetite. So at the base of this main zone, we've got a magnetic signature from the breakdown of the olivine in the troctolite. So you can see a picture of the troctolite on the right-hand side of these cores. At the top here, you can see the dominance of the gabbro-norite, melagabbro-norite, leucogabbro-norite, etc. Troctolite at the base of this gradational zone is very unusual. Van der Merwe, if I just go back one, Van der Merwe pointed out a troctolite in the main zone here, but the troctolite and the Waterberg deposit differs very much from the Van der Merwe's troctolite in that it's got a lot more olivine in the troctolite on Waterberg. So we've got troctolite at the base of this zone down here. The bulk of it is gabbro-norite, and when we go towards the top, we've got a very mixed package of rocks that includes everything from hartspigite to felspathic pyroxenite to anorthosite, as you see here. So there are so many differences between these rocks, this stratigraphy and the main zone, that we started to wonder whether we wanted to call it main zone. The orthopyroxene and plagioclase chemistry is more primitive than elsewhere. There are no significant pyroxenite layers as in the pyroxenite marker in the main zone elsewhere. And there's so many other geochemical differences that we ended up renaming this sequence. Instead of the main zone, we call this the TGA sequence for troctolite, gabbro-norite, and anorthosite. So looking now at the unit down here, the ultramafic series, below the TGA, there is a lower pyroxenite separated from the footwall by a series of marginal sills, and an upper hartspigite unit. Originally, the troctolite unit here was included in the ultramafic series, But we realized, based on thin section work and geochemistry, that there is a major break between the olivine composition and the fabric between here, and there's a gradation from the troctolite here up into an olivine gabbro-norite here. So we rapidly realized that the troctolite was part of this unit rather than the ultramafic sequence at the bottom. This lower unit, this ultramafic series, has more plagioclase than the lower zone. It's got about 10 to 15% plagioclase. And the Hartsbergite in this ultramafic sequence has a poikilytic texture rather than the granular texture seen elsewhere. There's kink bands and chromite lamellae in lower zone elsewhere, but not in the the Waterberg. And the aligned pyroxene crystals common elsewhere are missing. And the rocks, the chemistry of the minerals is less primitive than in the lower zone. So we concluded that it was more like lower critical zone. So we didn't want to call it lower zone, so we called it the ultramafic sequence. What is all this intruded into? Well, there's a footwall of granite gneiss, commonly a granophyllus, which is interpreted to be remobilized footwall gneiss interfingered with the pyroxenite. And what was all this intruded into? Because clearly the top of the bushveld here has been eroded away and Waterberg deposited along it. Marina Yudovskaya looked at a thin layer between the bushveld rocks and the Waterberg rocks and found very thin layers that had monazite crystals, zircon crystals, etc., which we've dated, and they're the same age as the bushveld. And we began to think that it was intruded into volcanic rocks. And recent work we've done has confirmed that suspicion. So what was so exciting about the PTM project is that they found PGE mineralization in the third hole that they looked at. And what they found was that there were two mineralized levels, a T reef and a lower F reef. And the T reef occurs at the interface between the TGA sequence and the upper zone. At its shallowest, it's 130 meters depth. And then they had an F zone, which occurs in the ultramafic sequence, and that shallowest is 180 meters depth. The, as you see from this map here, the T zone only occurs in the south. The F zone is much more extensive, extending at least 17 kilometers northwards. And what they've shown here is the super F zone, which is thickest and richest in what were sort of footwall depressions. And the map below from PTM is showing where their mining focus will be as they start mining. So when we look at the T zone, the T zone can be quite complex. There can be an upper T unit and a lower T unit separated by up to 35 meters of anything from olivine bearing feldspathic pyroxenite, pegmatitic gabbro, all sorts of things. And the key thing when you look at this is that the T-zone mineralization is always at this point. It doesn't matter whether there's a feldspathic pyroxenite, a Hartsbergite, an anorthosite, gabbronorite, it doesn't matter what the rock type is, the mineralization is at this interface between the TGA and the upper zone. And there you can see graphs of PGE plus gold here on the left, going through to the copper plus nickel plus sulfur in this graph here. So the take-home message for this is that the T-zone mineralization, irrespective of where it occurs, what lithology it occurs in, is always at this interface between the TGA and the upper zone, and that was picked up very rapidly using the magnetic susceptibility. So where the magnetic susceptibility suddenly started, that was where to look for your mineralization. So looking at the PGM, what is nice is that the grains are large and simple. Here you see, for instance, on this one, a telluride, but 90% of the area, based on the work done by my colleague Marina Udovskaya, is of platinum, palladium, bismuth tellurides. Then obviously these tellurides. And then what is very fascinating is down in the bottom right here, we show one of the gold-silver alloys, which are very common. And the grade in both the upper and lower part of this T-zone is the same at about 4 grams a ton, locally going up to 14 grams a ton in some cores. But what is so unusual is the metal ratio shown there in the pie chart of 50% palladium, 30% platinum, and 19% gold in the metal basket, with nickel and copper credits as well. So a nice simple mineralogy dominated by bismuth tellurides. Now, if we go to the F zone down at the bottom, it's only part of the ultramafic sequence. So here you can see in the purple, the Hartsbergite, interfingered by some olivine gabbronorite sills, and then down the bottom here, the phosphatic pyroxenite. So mineralogy in the T-zone, and again, sorry, you can see the PGE and gold grade here, very much restricted to this middle part, at close to the interface between the phosphatic pyroxenite and the Hartsbergite. And if we look at the mineralogy, whereas the T-zone was dominated by bismuth tellurides, the F zone is dominated by sperrylite with minor bismuth tellurides. But again, the scale bar on these most of these diagrams is 20 microns. This one is 30 microns. So again, you can see the grains are nice and large and simple. And there's a little bit more alteration down in the F zone, as you might imagine, with olivines, etc. down there. But again, the metal basket is very different, with 65% palladium, 30% platinum, and only 5% gold in the in this F reef. So if we look at the resource statement from PTM from September last year, based on a 2.5 gram per ton cutoff, we can see several things, and that is the dominance of palladium over platinum here for the T zone, and here for the F zone. We can see the elevated gold in the T zone, the upper zone, compared to the F, and we can see that the grade in the T zone is slightly higher overall than the F zone. That is important. And when you combine the resources, for the T and the F zone. Because the F zone is so much more laterally extensive than the T zone, the overall prill split shown here, where's my arrow gone? Anyway, you can see where the prill split is. Its overall is 29% platinum, 63% palladium, 1.5% rhodium, and 6.4% gold, because that's averaging all the F zone where the gold is much lower, and the high 20% of the T reef. Inevitably, we ask how similar this Waterberg deposit is to the Platte Reef. And currently, from the mineralogy done by Marina Yudovskaya, we can see a much simpler variation. This is just the F reef on Waterberg, but you can see it's perhaps much simpler mineralogy than through the Turf Strait reef that Dani is going to be talking about next. So how do we envisage all this happened? Well, we envisaged that early magma intruded as finger-like bodies between the footwall granifelts here and what we now think is volcanics. And as the more magma came in, it extended to a sheet-like body. And we think that the formation of the F mineralization was due to an intermix of the feldspathic pyroxenite and feldspathic quartzite accumulations. And then as the upper zone magma came in, shown here, we envisaged that the genesis of the TEORs is a result of the interaction between the first influxes of a fertile upper zone melt and a resident gabbroic melt. And when we look at the proportion of these elements, we can see that in the very northern part of the northern limb, there seems to be a similarity between the Waterberg, Harriet's, and Harriet's Wish, and it seems to contrast rather with the Platte Reef on Sandsloot, Turf Strait, and Hras Valley. And up in this area here, on Harriet's Wish, which straddles the Hout River shear zone, they have done quite a lot of drilling. And I've just chosen two of the holes that one of my students, Joseph van Schoutema, looked at. And in this particular hole here, they had mineralization in the what we would call the TGA, so that seemed to be similar to the T reef, whereas in this hole here, the mineralization seemed to be in a troctolite horizon with good grade, and they tentatively correlated that with the F zone mineralization. So when we look at a north-south cross-section, north to the left and south to the right, here we see the Hout River shear zone, and what we seem to have north of this Hout River shear zone is a much thinner succession of bushveld rock than to the south, but there seems to be more of a similarity between here and the Harriet's Wish Aurora section here, which lies to the north of this basement high. There seems to be more of a similarity between this area here and the main part of the northern limb to the south of that. So certainly when we compare metal budgets between the T and F zone with the Platte Reef, the Marensky Reef, or the UG2, it certainly looks like there is more similarity perhaps with the palladium-rich Platte Reef, although the mineralization occurs in very different stratigraphic settings. Now, we thought that the Waterberg deposit was very innovative, and clearly PTM were not crazy to drill where they did. But interestingly, I came across this map in a book by Ken, Cross and Dixon, and they had coloured a map from Vermaak and von Groeneveld in 1986. And you can see from this that way north of the exposed northern limb, Vermaak and von Groeneveld had actually predicted that there were these basic rocks under younger sedimentary cover. So many years, many decades later on, we've proved that they're correct. And I think from the work that Finn and others have done, this northern limb now becomes a major limb, and who knows, we might find more mineralization in other parts of this northern limb. I thank you for your attention.
Right, great. Thank you very much, Judy, for that very interesting talk. We'll open the floor for any questions. Please put your hand up, as mentioned before, and then unmute yourself when we allow you to speak. Okay, Danny, go for it.
I have to be first. Judith, very, very good talk. Excellent. I think the work that you guys and PTM have done was really important for the Northern Limb. It's a really interesting find, obviously, for all of us. The question, I've got many questions, as you know. The question I've got, how do I switch my video on? There. The question I've got is, a large part of this seems to go into the southern marginal zone of the Limpopo belt. Do you agree?
Yes.
And do you think there's a possibility that this could even extend further north, because the explorationists amongst us may find that quite interesting? And then the other thing is, when I look at the stratigraphic sequence that was established for this Waterberg area, and I look at the work that was done historically on Turfspruit, Ivanplatz properties on the open pit area, we see a lot of similarities in the lithologies and everything else, as I've discussed previously with you. So if you start to talk about this F zone, and maybe being lower critical zone, or even the lower part of the upper critical zone with UG2 and the MGs and those things come in, because you see the chrome coming in there. And then that zone above it, which is more noritic and autocitic, and then you go above that into the 2T zones. It really, to me, aside from all the contamination, obviously these rocks are contaminated because we're not seeing clear magmatic cumulative textures, things like that.
Danny,
It really starts to look at critical zone.
I'm losing track of what the questions are here.
Yeah, sure.
I just want to bring your attention to this map here. And this is where the edge of the bushveld is. And it goes, PTM has shown that it goes up all the way to the Palala shear zone. Yeah. Certainly, there's mineralization all the way up here. We might do some more work up here, but not surprisingly, because PTM need to get on and get mining, the focus has been here and about the first 8 kilometers, because that's where they're going to mine. But there are some holes from further north up here. So yes, it is quite extensive, and we know mineralization extends to 17 kilometers. Can you put into a simple question, because I've sort of lost the plot of what you were saying about your designated open pit area and what you saw there?
No, look, I'm just briefly, we're seeing the very same stratigraphic setup that you're seeing up there, from sort of mineralization closer towards the contact with the sediments or whatever is on the floor, and then a zone where there's basically no mineralization, which is noritic, gabbro-noritic, whatever you want to call it, into zones where there's a bit more peroxenite, and then those two T zones that you're talking about, which is very similar to what we've got here on the flat ring. So to me, that really, and I find it difficult not to see critical zone in that, aside from the contamination.
Okay, north of this Hout River shear zone, my research team has concluded that we're looking at a separate little chamber of the Bushveld complex that may or may not have been linked to further south. But certainly there are a lot more similarities between what we see in terms of the mineralization and the Platte Reef than there are in terms of looking at the Merensky UG2 or mineralization anywhere else. The problem is that if you look at this section here, there's probably the same sort of thing on the Aurora Harriet's. This would be Harriet's Wish here going just across in the Hout River shear zone. The problem being that it's so much deeper than the PTM property. Remember, on PTM property, the T zone is at its shallowest at 130 meters depth.
Okay, I'm not going to ask all the questions. Thanks.
We can have a discussion another time when we're able to move around. Coming up to Mokopane is highest on my list of travels once I can be unlocked.
Thank you.
All right, thanks. And yeah, any other questions, we'll keep the meeting open after all the presentations. All right. Thank you very much again, Judy. And yeah, any other questions, you can also message her privately or on the group chat. So thank you very much. Next up, as mentioned, is Dr. Danny Krobler, who will be talking to us on the Flat Reef deposit, Turkspruit, which is in the northern limb of the